For section 3.7, inverse trigonometric functions, we're going to look at this in a few pieces, a few chunks. This is from section 8.3 of the textbook Algebra and Trigonometry, second edition from OpenStax. I would encourage you to check out their textbook for lots of other resources and things. And a lot of these, and many of the diagrams and things like that will be there as well. So the objectives here are to understand and use the inverse sine, inverse cosine, and inverse tangent functions, to find the exact value of expressions using the inverse sine, cosine, and tangent functions, to use a calculator to evaluate inverse trigonometric functions, and to find exact values of composite functions with inverse trigonometric functions. Now, I'm going to go ahead right now and just highlight this last objective is, in my opinion, one of the most useful things that we can run into, particularly in Calculus 2. As you're doing trigonometric integrals, it's something that a lot of students just forget about. So it's important that we have that now. So as I record this video, it's a series of videos. These first two are first target we're going to hit. And let's see, actually, this will be the first video. We'll just talk about what these functions are. Then we'll worry about the exact values and calculator values, and then finally we'll come back to the composite function idea. So the domain and range of inverse trigonometric functions. So let's just think about how trig functions work. Trigonometric functions map from a domain of angle measure, so you say something like sine theta, to a range, an output of a ratio. So in the case of sine of theta, that maps to a ratio that is opposite over hypotenuse. So domain is our angle, output is our ratio. So inverse trigonometric functions work in the opposite direction, right? They start with a domain of ratio and a range of angle measures. So something like arc sine or inverse sine would be something like the inverse sine of the opposite over hypotenuse, that ratio, equals an angle theta. So let's take a few of these statements here. So sine of pi over 6 equals 1/2. That's certainly true. Cosine of pi equals -1. Again, certainly true from our unit circle. Tangent of pi over 4 equals 1. True from our unit circle. That means these following things are also true. Arc sine, or inverse sine, of 1/2 is equal to pi over 6. The inverse cosine of -1 is pi. And the inverse tangent of 1 is pi over 4. All right, so again, think about what this means is domain and range, and see if you can convince yourself that those things are true. They are, but take some time to think about it. So there is one issue with the idea of going from a ratio to an angle measure, and that is that angle measure is not actually unique. So if you think about the ratio found by cosine of pi over 2, okay, so here's our unit circle, angle pi over 2 is right here going on the positive y-axis, and the cosine of 5 pi over 2, well, 5 pi over 2 is 1, 2, 3, 4, right here, right? So that is 2.5 pi, that is. So it appears it's coterminal, really, is the issue. It's coterminal with pi over 2. So there are infinitely many other cases like this, other angles we can choose. So when we're trying to produce from a ratio an angle, how do I know it's pi over 2 versus 5 pi over 2? I really don't. But this is because sine, cosine, and tangent are not actually one-to-one functions. They're periodic. They're periodic. So we have to restrict the domain to an interval in which these functions are one-to-one. So I'm just going to think about what the unit circle looks like. We think about what this looks like on the unit circle. So sine has, in our case, we're going to work with these restrictions. Sine of x will restrict to -pi over 2 to pi over 2 with a range of -1 to 1. Cosine of x we will restrict to 0 to pi, again with a range of -1 to 1 in our x coordinates, and tangent we're going to restrict to -pi over 2 to pi over 2 as well. So sine and tangent and our cosine here. But again, these are areas in which the outputs, those ranges, actually don't repeat. So we're restricting ourselves down to this. Now, we really could choose any other interval as long as it meets those requirements. For instance, for sine, for restriction on sine, I could make pi over 2 to 3 pi over 2. That's fine. But these are the conventional choices. And so this is what your calculator gives you. This is if you're talking to anyone else about inverse trig functions, they're going to assume these things. So those are the restrictions that we're going to work with. All right. Those were the restriction that we're going to place on sine. Therefore, the inverse sine function, also known as arc sine, y equals sine the negative 1 power of x. It's not really a power. This right here isn't a power. It indicates that this is the inverse sine. So this means the domain, reversing those because we're talking about inverses, the domain is minus 1 to 1 and a range of minus pi over 2 to pi over 2. And as I said a moment ago, this is actually this restriction from negative pi over 2 to pi over 2 for our angles. These are actually values where the cosine is positive. It's not a coincidence. The inverse cosine function has a domain of negative 1 to 1, a range of 0 to pi, and these are values where the sine is positive. So our inverse sine is restricted to quadrants 1 and 4. Inverse cosine is restricted to quadrants 1 and 2. Arc tangent has a domain of minus infinity to infinity. If you remember, it has asymptotic behavior, and so that's actually what's happening there. And then the range is minus infinity to infinity. And again, that is restricted to quadrants 1 and 4. For the outputs of these, since they output an angle, they're going to be in those quadrants. Try it number 1. Given cosine of 0.5 is approximately 0.8776, write a relation involving inverse cosine. So if cosine of 0.5 is approximately 0.8776, then this means the inverse cosine of 0.8776 is approximately 0.5. Notice we are just replacing the input, or swapping the input and the output in that case. All right, so that ends this little segment of our notes. Be sure to go on to the next bit to find out how to evaluate with exact values.